A2 Maths, Motion Under Gravity. Okay, so what I'd like you to do, please, is just have a quick read of the situation with this ball and have a go at those three questions. Just to use in your year one skills, so stuff you've already practiced. Okay, so pause there, have a read and have a go. Okay, so let's see what you did then. So a ball is thrown straight up in the air. We've got an initial speed of 12 meters per second. The only thing acting on this ball is gravity pulling it straight down. So if you think about the situation, you're throwing the ball in the air, it's going to go up like this, gravity's going to start to pull it down, and it's going to come down, back down and land in your hand. So it'll go up, gravity pulls it back down, come back, and potentially lands in your hand or lands on the floor, whatever it needs to do. Okay, right, so the question is, first of all, is what's the maximum height this ball is going to reach? All right, so it's going to be thrown in the air, gravity is going to pull it back down. So at this point just here, it's going to start coming down. Now, what's important about the maximum height is if you look at the motion of the ball, it goes up, it hits the maximum height, and it's about to start coming down. But at that point just there, it's not going up anymore. It's about to go down, but it's not going down just yet. It's actually stationary. It goes up, reaches zero velocity, and then starts to come back down. Okay? And that's the key moment of when it's reached its maximum height, when its velocity going upwards is zero. So this is where we can boil it down to a Suvat equation. All right, it's all going to be down to Suvat. So we've got an initial velocity of 12 meters per second. We've got acceleration as 9.8. What's the maximum height? Well, we know that the final velocity is going to be zero, and we want S. So you're thinking v squared equals u squared plus 2as. There's no other equation we use. This one doesn't involve time, so therefore we can put the stuff we know in. We've got a final velocity, we've got initial velocity, we've got acceleration. We don't have a distance, but we can rearrange and get that. So well done. If you've got the maximum height of this ball, it reaches a height of about 7.35 meters. Okay, so if it reaches that 7.35 meters, the next question is how long is the ball above 3 meters? So it goes up in the air, it passes the 3 meter mark, it carries on going up to 7.35, it comes back down and then passes the 3 meter mark again and then falls below it. So the question is how long is it above that 3 meter mark before it passes again? Okay, so what information do we know? Well, we know the distance is 3. We know an initial velocity is 12. We know acceleration is 9.8 and we want a time. So we're thinking about which equation doesn't have a final velocity. We don't know what velocity it's travelling when it passes this 3 meter mark. So we're thinking of an equation that doesn't have velocity in, final velocity that is. And then what we do have is, because we've got the initial velocity, we can use S equals ut plus a half at squared. We can put the information in, so we know that's 3. When does it pass the 3 meter mark? We've got a u value of 12. We've got an acceleration of 9.8. So when we substitute all those in, notice we end up with, once we neaten it up, a quadratic equation. And a quadratic equation is going to give us 2 t values, which makes sense because one of them is when it passes the 3 meter mark on the way up, reaches 7.35 at the top, and then a second time is when it passes the 3 meter mark on the way down. So you end up with a quadratic equation and you end up with 2 times. Okay, it passes the 3 meter mark after about 0.28 seconds, and then it passes it again at 2.17 seconds. How long is the ball above that 3 meter mark? It will be the difference between these two. It's above that 3 meter mark at just under 2 seconds, 1.89 seconds a time. Okay. Right, look at number 3. The ball hits the floor 1 meter below where it's thrown. So it starts up here, it goes right up in the air, hits the 7.3 mark, comes back down, passes where it started, and then hits a point down here at 1 meter below where it's been thrown. Okay. How much time has passed from the ball leaving the hand to hitting the floor? So you're best off doing this one in 2 sections. You think I can work out the time it takes to reach the maximum height because I've got a maximum height already. So how long does it reach that maximum height? And then how long does it take to travel back on itself from that maximum height plus an extra meter underneath? So how far is it going to travel on the way back down? 8.35 meters. It's got the extra meter. So how long will it take to travel 8.35 meters? Okay, so we're going to do it in two sections. Time taken to reach the maximum height. We've got initial velocity, we've got final velocity, because we know each is 0 its maximum height, plus acceleration times time. So v equals u plus at. Rearrange it, get your time. It takes about 1.22 seconds to reach the maximum height. Once you're at the maximum height, we can do a separate equation now. We can say, right, our new velocity is going to be 0 because it's just about to start coming down. Acceleration is pulling it downwards, so we've got 9.8 pulling it downwards. We also got a distance of 8.35, but we don't have a final velocity here. So we've got initial velocity of 0, we've got a distance of 8.35, and we've got an acceleration of 9.8. Okay, so we've got this situation just here. We've got that bit just there. We've got this bit just here. Just be very wary. I've just mentioned what's going on here. If you're taking, whenever you do these things, you've got to consider these are vector quantities. In other words, if you're working upwards and up is your positive direction and the ball is going to start coming down, then it's traveling a negative distance. It's coming down with a negative distance. All right. Now that's fine as long as you're aware that gravity is also pulling down in the same direction. Gravity is pulling down with a negative direction. So it's fine here. It pulled down here, but we've also got it set up as pulling down here. Now, you don't have to do it that way around. You can take downwards as positive, in which case you could use 8.35 and 9.8. But it's absolutely vital you consider which direction you set as positive. Because for this one, the 12 was going upwards, so it's positive, but the 9.8 was going downwards because acceleration was pulling you down towards the Earth. So always consider which direction you're traveling, okay, whether it's positive or negative. Right, so once we've got that, rearrange it, t equals 1.3. If you've got those two both positive, you would have got exactly the same time in this case. All right, so we've got 1.22 going up, 1.3 seconds going down. That makes sense because it just takes a little bit longer to come down. Put them together, total time of 2.52. Okay, right, so those questions should have been absolutely nothing new. All right, you practice those in your year one, but it's good practice ready for what we're going to look at, which is what happens in 2 dimensions. What happens if you don't just throw a ball up in the air, but if you throw the ball off at an angle? Okay, so if a ball is thrown at an angle of 60 degrees with an initial speed of 12 meters per second, so instead of me throwing a ball straight up in the air, I'm going to throw it off at 60 degrees like that. Okay, taking acceleration due to gravity is 9.8, so gravity is still pulling it down, and the point where the ball leaves the hand as a height of 0. All right, so we can use that as our starting position. What I want to do is I want to look at modelling that situation. So I've got, here's the ball, it leaves the hand at 12 meters per second, an angle of 60 degrees. So what I'd like you to do is just have a think, what would happen to the ball after it's thrown? Okay, so pause there, have a good think about it. Okay, so what would happen to the ball after it's thrown? Well, you expect, because you're throwing it and you've thrown balls or you've hit balls before, so you know what happens. The ball will generally go up in the air, and then at some point it will start to come back down until it hits the floor, and it will do this sort of shape. Okay, so it will come up, it will reach its maximum height, and then it will start to come back down again. And as you know, this is what we call a parabola shape. Okay, very similar to a minus x squared curve, obviously moved up a little bit, but it's that sort of parabola shape. And that's exactly what the ball will do. Okay, the ball will go up, gravity will take effect, start to pull it down, reaches its maximum height, gravity pulls it back down. Exactly the same as what you just seen, but if which was going up and down in just 1 dimensions, but in 2 dimensions it does exactly the same, but it forms this nice parabola shape, just like that. Okay, right, so with this time I do want you to pause again. I want you to think about what assumptions you have made for that to be true. To make a perfect parabola shape, what assumptions must you have made? So just pause it there, have a think about it. Okay, so there's 2 really obvious assumptions you should make. And the first one is to do with the ball being taken as a particle. And we say that quite a lot with your applied maths. We take the item as a particle, whatever it is. Doesn't matter whether it's a train or a football, you take it as a particle. And there's a couple of reasons why you can see in this case, all right, why we take it as a particle. One of the situations is that you don't have to worry about its size. All right, you don't have to worry about its size at all. And if you don't worry about its size, that means you don't have to work out its center of gravity. It means you don't have to worry about things like spin. Okay, so a difference between a situation like hitting a shuttlecock compared to hitting a tennis ball, compared to throwing a rugby ball, compared to kicking a football. They're all the same because you're taking each of those items as a single point. So you don't need to worry about its size and you don't need to worry about its spin. Okay, they all act exactly the same ways. And the other thing you should be aware of is there's no other force acting on the ball. Okay, the only force acting on the ball is gravity. Now, the common one that you work with is, of course, air resistance. We can ignore any sort of air resistance. And again, if you think about something like a shuttlecock, they're designed so they go up like that and then they fall very quickly if you play in badminton. Okay, whereas a golf ball is generally not worried about air resistance at all. They're designed like that, so they will form a beautiful parabola shape relatively nicely. Javelins are the same. Javelins will generally go up and then screw back down again. So you can ignore all of that because you're not worrying about being a particle. Okay, so you're concentrating on being a particle and you're ignoring any other forces. Difference between, for example, firing a cannon. Now, when we talk about firing a cannon, we fire a cannonball. Now, the cannonball will form a parabola shape. Whereas if you fired something like a rocket, that's different because once a rocket takes off, it still has a propulsion system. It still has another force, which is the thrusters pushing it up and out into space. Okay, so we're not looking at anything like that. We look at cannonballs because once you fire the cannon out, there's no other forces acting on it. Okay, bullet from a gun would be the same. Once you fire a bullet from a gun, it's just a piece of metal. It will just fall back to earth. Okay. All right, quick question. That example we talked about was a tennis ball. Okay, it could be a tennis ball. What difference would it make if I changed it to a bowling ball? So what difference would it make to that shape if it was a bowling ball? So just pause there, have a think about it. Okay, so the common misconception, the common mistake people make is thinking, right, well, because it's a bowling ball, because it's heavier, what's going to happen is it's just going to generally fall back down to earth really quickly. All right, it's going to go like that. Okay, or you might think it lands in the same place, but it does it in a lot more shallow way. Okay. Whereas something like a tennis ball or a ping pong ball especially, will be doing that. Well, they don't do that because they are still leaving at 60 degrees. So the bowling ball is not going to do this because that's not leaving at 60 degrees. And if it does leave at 60 degrees and does shallower, you're talking about doing that. But it doesn't do that because it's leaving at 12 meters a second. Now you imagine you're trying to throw a tennis ball. It's very easy to throw a tennis ball at, let's say, a speed of 12 meters per second. But to do it with a bowling ball, you're going to have to use a lot more effort. It's going to have a lot more inertia. So what's going to happen is the bowling ball and the tennis ball will form exactly the same parabola. All right. It does not make any difference about mass. All right. The mass of the object makes no difference at all. All right. So you can ignore any questions to do with that. It makes no difference. All right, so don't start making this idea that even if you're, say, for example, driving a bus off a cliff, no difference between that and kicking a football off a cliff. They're exactly the same. Okay, if they leave the cliff at exactly the same speed. Right, so both balls will hit the floor at the same time, and both balls will make the same pattern if they left under the same starting conditions. Okay. So what I'd like to look at on this one is just the X position. Now this is imagining if you're looking at this is a football, let's say it's a bright yellow football, you can clearly see it, but you're looking straight down from, let's say, a tall block of flats or an aeroplane or a helicopter directly above it. So you're far enough away so that you can't see it going up and down, but you can clearly see it moving across. Now what I'd like you to do is just watch this circle just here. Okay, now the circle on the top shows the motion of the ball, but the circle on the bottom would be how it appears if you were looking straight down at it. Now, if you concentrate on that one, forget that one for a minute. Just look at the big circle for the last part. So as the motion carries on, just watch this circle just here. And you'll notice that if you just watch that circle, it looks like it moves in a smooth, constant rate. And that's exactly what it does. In the X position, because there's no forces acting in this direction, in the x direction. Nothing's slowing it down, nothing's pushing it along. What happens is, because we've got an initial velocity, it just carries on with that same initial velocity all the time. And the only reason it stops is because it's ploughed into the ground. All right, so all the way across in the x-axis, it keeps a constant rate. There is no acceleration speeding it up. There's no acceleration slowing it down. It has no acceleration in the x direction. It stays that constant rate. Okay, let's do the same thing, but this time looking at the y position. So watch the big circle. As the ball goes up, all right, we can see it goes up, it reaches the maximum height, and then it starts to drop back down again to Earth. So if you looked at it from this position and you couldn't see depth at all, what you would see is the ball just being thrown in the air and coming back down again. All right, that's exactly the same as what we dealt with on the start of the lesson. The ball goes up, gravity takes effect, ball comes back down again. So what we can do is we can split it into two different directions when it comes to these, exactly the same as what we did earlier with different mechanics problems in 2D. So if we're looking at a 2D problem, we can look at considering going in the x direction, and we can look at considering it in the y direction. And if we can split it into those two directions, it means we can be able to figure out things like what's its general position at certain times, what speed is it traveling at certain times, when does it reach the maximum height, what is the maximum height, when does it reach the ground. We can do all sorts of maths as long as we consider it in these two separate directions. Okay, so just grabbing your notebooks then. Let's just put some notes down in our notebooks. These are the important facts that you need that an examiner could ask you in the exam, just the small one markers. And it also goes into how we go about solving these questions. So if a particle is projected in the air and its weight is the only force acting on it, so it's got a weight, and because it's got a weight, gravity is pulling it down. Okay, that's the only thing that's got affecting it. There's nothing to do with air resistance, there's nothing to do with spin or anything like that. It's just gravity that's pulling it down. And what that means is that you're only changing the y-axis. Nothing in the x-axis changes at all. There's no acceleration. Now we can write that as a vector. So when we write it as a vector, because the vectors can be set up as x, y, okay, there's no except gravity, we can write our acceleration as 0 minus g. So when we consider what the acceleration is, there is nothing acting in the x direction, so there's nothing in the I, and in the j is minus g. So nothing happens across, gravity pulls it down in the j direction. Okay, right, we also want to make sure that when we plot projectiles, you know the shape. They always form this nice parabola curve, and you could sketch that curve down nice and neat. But what we need to be aware of is that they can change these about slightly. So your projectiles, whenever you do projectiles problems, they always form either a nice neat parabola like that or part of a parabola curve. All right, we can see that's part of a parabola curve already, but you might have different sections of it. So this example could be a cannonball being fired on a flat field, takes off, flies in the air, lands exactly the same height as what it's taken off as. Okay, but you might have different types of mechanics problems. I don't expect you to draw these down in your notebooks. So you might have a situation where you have a javelin. Now, javelin leaves the person's arm at a height of 2 meters. All right, if you're looking at the point of that javelin, it flies up in the air and then flies back down and stabs into the ground. Now, it stabs back into the ground at a lower point than when it's taken off. Okay, so you get that section, and you need to consider some differences there. It hits at a different height to what it's taken off at. You might get a situation where it does the opposite. It fires on the ground and then goes up and hits, let's say, a net. If it's a basketball problem, you throw the basketball in the air, it goes in the air and then lands through the basket. You might have a ball being kicked on a roof. Okay, you've got different situations, but if you notice, you still get this nice parabola shape. Okay, and the other one that's quite common is situations like this. Okay, if you imagine that you kick a rock off the top of a cliff, then what happens is it comes off the top of the cliff and it's traveling straight across in the horizontal direction. All right, you didn't kick it up in the air, you kick it directly off the cliff, so therefore it travels like that. And the other one you get with this is if a tennis player hits a tennis ball. As you know, he throws a tennis ball in the air, then he whacks it. At the moment his tennis racket hits it hits it exactly horizontally. So look for those sorts of key things, because although they seem different, they're all the same type of problem. They're all projectile problems. And because of all projectiles problems, they all share this in common. The acceleration is always 0 minus g. So what that means is we can use that fact. We can use that fact to help us. Okay, so if we know this one key fact is always the same for projectiles problems, that acceleration is taken as 0 minus g, what we can do then is we can use that to work out our velocity and displacement equations. So we know from last lesson that if we got an acceleration and we want to work out a velocity, what we can do is we can integrate it. So if we integrate the a vector, what we're going to end up with is clearly 0t, just there, and minus gt here, because we're integrating it in terms of t. So I'm going to get 0 and minus gt. But we also have a starting velocity as well. Okay, now the starting velocity will come from when we integrate, we end up with a constant. And we know that when t equals 0, the initial velocity is going to equal ux and uy. So that's our c value in a sense. Okay, so if I got this bit just here, it's going to go to 0t plus the constant of integration, which is where the ux comes in. This one will be minus gt, but the initial velocity is going to be uy. So I end up in this velocity vector. Now the other option you might notice is that this is a Suvat equation. And we know that if we want to use Suvat, we have v equals u plus at. Now if you look at the top line, all right, v equals initial velocity in the x direction plus acceleration times time. Now acceleration in the x direction is 0, so that's just 0t. The bottom line, v equals initial velocity in the y direction this time, minus at. Acceleration is minus g, t. So I'm really using v equals u plus at. So that's exactly the same as integration. It's nice to see exactly the same coming out from that Suvat equation as it does with integration. Okay, right, so I've got velocity. Okay, so as long as I've got an initial velocity there and there, I can work out velocity. Can I use that to get my displacement? Yeah, I integrate it again. If I integrate it again and I take my initial position as 0, 0, okay, I could have different start positions. My recommendation to you is always to start at 0, 0 as your starting position. Okay, always to start at 0, 0. Then what you end up with is you end up with your position vector like this. And again, if you look at the integrating it, so we've got ux in terms of t, that's why we've got uxt. We've got uy integrated in terms of t is going to go to uyt because that's just numbers. Gt in terms of t, well, we're going to get t squared over 2, which is where that comes from. Or forget the integration, look at it as a Suvat question. R is a position. S equals ut plus a half at squared. Now for the top line, u is the initial velocity in the x direction, so it's ut plus a half at squared, but there's no acceleration in the x direction, so there's no at squared. Bottom line, s equals u in the y direction, so that's just uy, t, so ut minus a half at squared. Acceleration is minus g in this case, that's why we get minus a half gt squared. So we've got both of those equations either through integration or by using Suvat. It doesn't really matter. All right, they're both linked, they're both exactly the same. Some of you might prefer to think of it as Suvat equations though. What's important here is sometimes you might have a situation like, for example, the javelin thrower thrown at 2 meters high, and people think, oh, I'm going to use one of these as 2, all right, as an initial position of 2. My recommendation is to always start at 0, 0, and the end position could be negative. So you could deal with a negative value of where it ends. So if it drops below where you started, you could have a negative value. All right. If you're kicking off a cliff, for example, Top of the cliff could be 0, 0. Hitting the bottom could be a negative value. There's nothing wrong with that at all. In fact, it's a lot easier to work with. Okay, so let's go back to that original question and just look at a slight problem we've got. So that ball was kicked at an angle of 60 degrees and has an initial speed of 12 meters a second. But we've just talked about making it in terms of x's and y's. Now the problem with x's and y's is that this clearly isn't in component form. We don't know how far the x is, we don't know how far the y is, right? What the velocity is for both of those directions. So that's what I'd like you to consider first of all, please. So just pause there, have a consider how you work them out in component form. And if you want a hint, I'll give you a hint first of all. Okay, so your hint is this. There you go. So pause there and see if you can work it out. Okay, so hopefully you thought about using trigonometry. If we've got 12 meters per second at an angle of 6 degrees, I can work out how far it is in this direction, what speed it would be in this direction, and I can certainly work out the magnitude of the speed in that direction. I can work out the size of the speed in both of those directions. So I can do that using basic trigonometry. 20 connected. One's connected to this side, so it's cos. So 12 cos 60, whereas this one is separate from the angle, so this is just sine. Sine is separate from the angle. So 12 sine 60, connected, separate. All right, so we've got those two just there. So I could calculate those. Okay, so when t equals 0, when we're first starting at t equals 0, the initial velocity would have been 12 cos 60 in the x, 12 sine 60 in the y. So 6 and 10.4. All right, so that is my initial velocity. That's my ux and my uy that I'm going to be using. All right, velocity in the x, velocity in the y. Okay, so now we've got our ux and our uy. What we want to do is we want to write out the general form, all right, the vectors for not just the initial velocity, but also for the acceleration and the final velocities and the position. Now we can do that by always starting in the same position. Let's write down acceleration. This bit here is identical for every single projectiles question you do. Regardless of all this waffle up here, it always does exactly the same. Acceleration is 0 minus g. Okay, for every single one of these questions. And it's worth writing that down because you never know, that may be one of the marks. Once you've got your acceleration written down, what we can do now is we can write out velocity, either by thinking about the integration, either by remembering off the top of your head, or by doing Suvat, v equals u plus at. Okay, and what we're going to get is v equals u plus at. There's no acceleration in the x direction, and v equals uy minus gt. These are exactly the same, but we can fill in our ux and our uy in this case. 6 across, 10.4 up. So I've got my velocity equation set up. And the last equations I want to set up is my distance equations, the position, the displacement, I should say, the displacement equations. And that would, you get those through using s equals ut plus a half at squared. Okay, but the general position, because it's vectors, is r equals uxt, uyt minus half gt squared. And as I said, some of you will just learn these off the top of your head and then just fill in these two parts. So we've got the 6 and the 10.4. So being able to formulate these equations for every single one of these, it doesn't matter what they ask us now, whatever questions they ask us, it's going to be using these equations just here. Having these equations set up ready means that whatever question we get given, we should be able to just pick out the correct one and use it. You also, if you can set up these equations, you've got a very good chance of getting a few of the marks already in the bag. Okay, because you've already set up your Suvat equations ready to go. Okay, so what I'd like to do is I'm going to put up 3 questions. First one is, what is the ball's position after 2 seconds? So you can consider what would be the ball's position, there's your hint, in 2 seconds time. The other next question I want you to consider is, what is the time and the position of the ball at its greatest height? So when it reaches this greatest height up here, what's the time? What's the position of it? So in other words, what's its position across and up? And then finally, I want you to consider what is the time and position of the ball when it reaches the ground just here. So how long is that time of flight, and what's its general range, it would be called. Okay, right, so I want to pause there. I want you to have a go at all three of those. All right, so do any ones you can. And if you get stuck, it doesn't matter. We're going to go through them fully. But I want you to pause now, have a go at those questions. Okay, so let's have a look at question number 1 then. So what's the ball's position in 2 seconds? So if we're looking at the ball's position in 2 seconds, we're looking at which is its position vector. Now the position vector is the bottom one. So I could write the position vector straight out, and all I need to do is, because I want the position after 2 seconds, you know, if I think of it as a grid, how far across, how far up, all I need to do is put the number 2 in, so 6 times 2 would get me 12 across, and 10.4 times 2 minus a half g t squared, where g is 9.8, I can fill that bit in as well, I would get 12 and 1.2. So after 2 seconds, the ball's going to go up, it will stop there, that's 2 seconds, and we can see it's 12 across, 1.2. Again, you guys that prefer Suvat, all right, and you may have seen this if you've done either GCSE work with Suvat or if you do physics now, you might find it easier just to do a separate equations. No problems with that at all. You don't have to do it with vectors, but most of you will find vectors easier to understand when we come to some harder algebra questions later on. Okay, so just be aware of that. But if you want to use previous skills to do these problems, it's exactly the same, as long as you get the right answer. Okay, so we've used the position vector. Let's have a look back at that second question. If you need distance, just a very quick mention, just in case they ask you this, how far is it from there to that ball? Maybe it's landed on a roof or something like that at that point, and what's the total distance you have to travel to get there? Well, in this case, it will be Pythagoras' theorem. 12 squared, 1.2 squared, all square rooted. Okay, so you could be asked a question like that, distance of 12.1 meters, 12.1 centimeters, whatever it is. Okay, it'd be meters in this case, of course, because we are dealing with meters up there. Okay, so let's go back and look at number 2. Okay, so for number 2 then, let's have a look what it's asking. It's asking us what's the time and position of the ball at its greatest height. Now we've just done a question like this at the start of the lesson. When we consider the greatest height, let's just think about what's actually happening here. The ball is going up, reaches its maximum height, and then starts to come back down again. Now, if we think back to the start of the lesson, we have already done one of these. Forget the x direction for a minute, because the x direction doesn't really know when it's reached its maximum height, because all it does is travels across at exactly the same rate. It doesn't care where it is, it's just going at the same rate all the way across. But the velocity in the y is different, because the moment you take off with a velocity of 10.4 going up, what's going to happen is you're going to slow down, slow down, slow down, slow down, stop at the top, and then you're going to coming down because gravity pulls you down. So although this way carries on at 6 all the way across, anytime you stop it, 6 meters per second across, 6 meters per second across, it continues at 6 all the way across. But upwards starts with its maximum velocity of 10.4, goes to 0, and then comes back down and reaches 10.4 minimum velocity, and velocity again at the bottom. So the question is, which one of these is the important one for working out the greatest height? Well, the answer is the velocity. Definitely the velocity. That's going to help us work out the maximum height, because the velocity equals 0 in the y direction. So we're looking at this point just here, which we just said. It's not a position just yet. We're using the fact that when it reaches its maximum height, it's no longer moving upwards. So its maximum velocity, so its velocity in the y direction is going to equal 0. Obviously, the velocity in the x direction is still at 6. It's always at 6. But the velocity in the y direction has gone up with 10.4, stopped, and is now coming down. So I know this fact. I pick out the velocity. I pick out the velocity in the y direction. I write it down, and there I go. Now I just need to rearrange and solve it. So take the GT over that side, divide by 9.8, out pops 1.06 seconds. Now, once I've got the time at the maximum height, I'm back to question 1 again. I've got a time, what's its position? All right, what's its position at that greatest height? I've got the time of 1.06. So what's its position? Stick that value into there and there. And lo and behold, we get this equation, our position equation, and we can substitute it into all those places, and out pops its position. 6.37 across, 5.52 meters up. That's the position at its greatest height. Okay, so well done if you managed to get that. Okay, so let's have a look at question 3. Okay, so for question 3 then, what is the time and position the ball hits the floor? So the first thing we need to do is make sure we have an assumption. The ball is hitting the floor at exactly the same height as when you launch it. So if the height has started to increase, reached its maximum height that we just saw, and then starts to come back down, the key thing about where it hits the floor just here, it has a height of 0. So what you need to be considering is which of these represents the height. Right, it's clearly not the acceleration. It's not velocity, that doesn't represent height, but the position represents height. This represents its distance across. This one represents its height at any given point. So what we're looking for is this bottom equation when s equals 0, okay, when u equals 10.4 and when acceleration is minus g, we're using this equation to work out when it hits the floor like that. So we pick out that equation, we're going to set that equal to 0, and we get a quadratic. It's a nice quadratic though, because it's just going to be a case of easy rearrangement because it's equal to 0. There's no c value. So we get this. So we get two answers here. We get t equals 0, which is interesting, and we get another value coming out when I rearrange this equaling 0. So when that equals 0, I get 2.12, but don't forget the t equals 0, that's important. Where does that t equal 0 come from? Well, that t equals 0 is the other place when it has a 0 height, which of course is the starting position. Okay, so there's your starting position just there. You both shared a height of 0 then. But the one we want, of course, is 2.12. What's its x position at that time? Take your time, substitute back into position vector. 6 lots of 2.12 is going to get you 12.7 meters. So if you're asked a question to do with how far has it traveled, all right, when it hits the ground again, what's the distance to the ball after it hits the ground, you do exactly that same thing. Forget the across direction, you take the up direction set to 0, and then once you've got that, it gives you a time and you can substitute it back in to the one you want. Okay, so just go back to your notebooks then. We're going to look at an exam question on this. So I'll give you an opportunity just to take down some key facts in your notebooks. And also, it might be worth just thinking about how to do this yourself. So you might want to have a go yourselves. Okay, right, pause it there. Make sure you've got enough time to both copy it down and have a go, and then we'll have a look through it. Okay, let's see how far you got then. So the catapult is being fired at a height of 1.5. So imagine you're stood up and you're firing a catapult, not like a big giant catapult, one of these ones you hold in your hands. All right, so catapult you're firing from your hand. So we fire this catapult and you're launching a stone out of it, and you're doing it pointing horizontally. So initially, the stone is going to travel in a horizontal direction. So you're firing it like this. Okay. So the moment you fire it, of course, that stone is going to start to come down. Okay. Right, what happens to that stone then? So on its way down, it's being launched into a flat field. Right, that's important. So it's not bumpy, it's not like that, it's not got different heights, it's a flat field. It travels towards two different walls. Both of them are a height of 1 meter. Okay, so you've got two 1 meter long high walls. The first wall is 10 meters away. Okay, so it's 10 meters away, and the second wall is 20 meters away. So if you haven't sketched that situation already, that should have been the first thing you did. Just doing a rough sketch of the situation, and the rough sketch should look something, all right, to do with like this. So a stone is fired parallel with the ground with initial velocity only in the x direction. Okay, so we know that initially its velocity is u in the x direction. You could just call it u if you wanted to in this case because there's no y's, and 0. So u in the x direction and 0. That's what we know that we just talked about. Can we sketch it then? So we're going to sketch the situation and we're going to write down our general equations, as you should always do whenever you get to these type of projectiles questions. Okay, so I'm firing the catapult like this. Okay, I'm going to draw my walls in just so I've got an idea. So I've fired it straight across. Okay, at 1.5 meters high. Once I've done that, I know that 10 meters across, there's a wall 1 meter high. And at 20 meters across over here, there's another wall of 1 meter high as well. Okay, now what's happening? It's observed the stone travels over the first. So it definitely travels over the first one. So that's like its minimum velocity, just gets over that first one, but does not reach the second one. All right, so it doesn't go over it, it doesn't hit it, it just doesn't reach it. So it lands somewhere in this region just here. It just clips that first one and lands, or it goes way past that first one, but it doesn't get as far as hitting this one. That's the two things I know. So what I want to do is I want to find the possible speeds. So I'm looking for UX. So I need to make sure I'm aware of the minimum speed. That would be the one that just clips that. And the maximum speed with one where it well clears that, but just maybe touches the bottom or lands right at the bottom of that wall. Those were the two extremes of these catapults. Okay, so it's that one that just clips the top. Right, so I'm definitely looking at it as being greater than that, but also the one that touches the bottom of the wall. So I'm looking at the one just a little bit less than that. So I'm looking at a greater than that one and slightly less than this one. Okay, and any speed between that would obviously get to land anywhere between those two. Okay, so how do I go about working out these two speeds then, if that's the only thing I don't know? Well, what I do know, of course, is this is a projectiles question. That stone does not have its own little thruster pack on it. It's falling under gravity. So therefore, straight away, as soon as I recognise it's a projectiles question, I'm going to write A equals 0 minus G. Okay, I'll get my acceleration written down straight away. I'll write down my A values in the X and in the Y directions. If I've got my acceleration, I can then write down my velocity. Now my velocity is interesting because normally I have a UY there, but of course UY is 0. So I don't even bother putting that in. Okay, so I've got UX and 0 for UY. V equals U plus AT, but the initial velocity is 0. It's not going up or down to start with. What about its position? So its position is going to be UT in that one. And for this one, I'm putting in 1.5. Okay, that contradicts what I said earlier on about always starting at 0, 0. And I'll come back and talk about that in a second. But I want you to be aware that this might happen because you might have an examiner saying, show that the initial position is this. And I don't want you to only consider 0, 0 as the only possible solutions. So consider this one being a show that. If you'd gone with 0, 0, and therefore you were looking at minuses, okay, minus 1.5, that's perfectly reasonable. There's nothing wrong with that. And in fact, in some ways it make it easier because this equation here would just be minus a half GT squared. Okay, so there's nothing wrong with doing it either way. Take that as 0, 0, and you're looking for minus 1.5s. Or take that as 0, 0, and your initial position is 1.5 up, which is where that bit comes from. Okay, up to you. Don't feel you have to do one or the other. Okay, so I've got this bit set up now. Okay, so you're either the same as me at 1.5 or that's 0, in which case it was just minus GT half GC squared. Right, so now I can actually think about the problem. Okay, so if we look at the problem, we're going to look at almost like two separate paths. We've got this minimum path just here, that's flashing there, and we've got this maximum path, which is just there. Okay, so what I want to do is I want to separate these two things up. So the first one I'm going to look at is the minimum path, the one that just clips the top of that wall and then flows down. All right, so it literally just touches the top of that wall. All right, in fact, in this case, it just lands on top of the wall. So how could I do that? What do I know about it just touching the top of that wall? Well, that is the answer, isn't it? If it's just touching the top of that wall, that point there at the top of the wall is part of its flight path. It's a position that it's reached. That ball, that stone that's being fired out, reaches a position 10 across, 1 up. So if it reaches a position of 10 across, 1 up, if that's its position, 10, 1, that is the same as that vector just there. When is that vector just there? 10, 1. And again, you could do it with Suvat if you want to. You can consider just the up part. When does it reach a height of 1 meter? That's what you're looking for. When does this reach a height of 1 meter? So that's what we're going to look at. There's its position. Can we then solve this first equation? When do we have a height of 1 meter? So the stone comes down, reaches a height of 1 meter. I can solve this then and get t equals 0.32 meters per second. That's its velocity, that's its time. Sorry, not meters per second, 0.32 seconds. At 0.32 seconds, what would be the initial velocity? But you know that ux, velocity in the x direction times time, has got to be equal to 10. So therefore, if I substitute that into this equation, and I'm going to rearrange, I get my initial speed of 31.3 meters per second. If it's greater than 31.3, it will just be fast enough to clear that point. If it's slower than 31.3, it's going to come down and hit the wall early. If it's exactly 3.3, it will touch the top of the wall perfectly. Okay, so that's the top. Sorry, that's the minimum speed it has to travel to just clear that wall. Okay, so let's make a note of that. So it just clears the wall if it goes 31.3 across, 0 up and down, of course. So I can make a note of that. Its minimum speed that it needs to be taken off with is 31.3. So there we go. Right, its maximum speed, though, on the other hand, is when it's just about to hit the bottom of the wall. So let's consider that one as well. So its maximum speed is looking at this situation just here when it touches the bottom of that wall. So if I consider that point just there, when it reaches the bottom of that wall. So if we consider that point just there, what I can do is I can do exactly the same bit of maths I just did. I know its position is going to be 20 across, 0 up. So when is this equal to 20, 0? So when's that equal to 20, 0? Well, I can set that y position equal to 0, okay? And I'll end up with 1.5 equals a half gt squared, and therefore I get my time. Now, for you guys out there that decided on 0, 0, then you're looking for when is it equaling 20 across minus 1.5 down. So from 0, 0, we'll go to minus 1.5 down. And you'll notice that you get exactly the same answer, because what you would have got is minus a half gt squared equals minus 1.5, which gets you exactly the same answer as this, of course. All right, so there's no difference. And if you prefer to start at 0, 0, that's perfectly acceptable. There's nothing wrong with doing that at all. All right, you might prefer it. Okay, so I've got my time. What do I do with my time? I substitute it into the top one. And from there I can get my other speed. Okay, 36.1, which I know is a velocity of 36.10, but its final speed is going to be 36.1. If it's exactly 36.1, it will just touch the bottom of that wall. It will literally hit at the bottom of the wall. So it has to be slightly less than that. So any speed between these two vectors, values just here, these two speeds just here, will allow it to clear the first wall but not hit the second one. So well done if you managed to get anywhere close to those answers. Okay, so what I'd like you to do is I'd like you to have a go at these multiple different exercises. There's lots of different exercises on there. Do not rush them. Projectiles are usually worth big marks in that exam. So it's making sure that you're practicing writing those equations, using your other skills. If you've got your GCSE skills or your physics skills and you'd rather use those, that's okay. Keep checking you get the correct answers though. I don't mind which technique you use. Okay, so have a go at all those and let me know if you need any help. Okay, so what we want to do is we want to look at a more algebraic situation. So rather than us putting numbers in, some of the harder projectiles questions out there will come in the form of purely algebraic questions. So what we're going to do is we're going to look at a few of those. So there's my projectile. It's going across and it's going up with initial speed of ux and uy. So nothing different there. But what's important about this one is that I'm not going to give you some values to substitute in. What I am going to do is expect you to work out acceleration, velocity and position in terms of ux and uy. Okay, and hopefully you can fill those in yourself. Okay, let's see if you filled them in yourself then. So acceleration is always the same. That's your starting position. You always get the same acceleration. Your velocity is always the same then, ux and uy minus gt, you're using v equals u plus at there. And your position vector at the end is r equals uxt or uyt minus a half gt squared, using s equals ut plus a half at squared. So these equations, for most of you out there, will probably see these and learn these off by heart. Okay, and you can just fill in whichever information they've got. Right, but what happens if it's purely algebraic then? Well, what I want to look at is a couple of questions. If I've got that as my theta value, I don't know what angle it is. Notice there's no numbers on there at all. I don't have an initial speed. I don't have an angle. So these are general terms, u and theta. What I'd like you to do, please, is write ux and uy in terms of speed and angle form. Okay, so just have a go at that. Okay, so hopefully you got that ux was connected. So that's the theta, so that'll be u cos theta. And this one is separate from theta, so this will be your uy equals u sine theta, using your SOHCAHTOA from GCSE. Okay, so hopefully you got both of those. Now I've got both of those, I can fill those in all these spaces here. Okay, so u cos theta, u sine theta, u cos theta there, u sine theta there. So I can fill all those in. Okay, so there's my general equations now, using this is my initial u in the x direction, this is my initial u in the y direction. So I've filled in all my Suvat equations just there. Right, what I want to do is work out the total time of flight then. How long does it take to travel from there to there? I want a general equation so that I could just fill in the information. So what's important about the time of flight? Well, we know that if I look at the projectile going up, reaches the maximum height, come there, comes back down, at that point just there, it's got a height of 0. And that's the key thing, that when you actually hit the ground at the other end, its height goes up, 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 down, 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 reduces back to 0. So I'm going to use that fact. At the time of total flight, the height part, which you know from here, is going to equal 0. What's the height part? That bit just there. ut sine theta minus a half gt squared. So I can use that fact. 0 equals ut sine theta minus a half gt squared. I can simplify that, can't I? I can factorise the t out. That initial t makes sense because that's when the starting height is 0. So I can ignore that one. I don't want that. I want the time it takes to hit the ground the other side. So that's when u sine theta minus gt, minus a half gt, is equal to 0. Again, I could just do a bit of arranging, couldn't I? I could times everything by 2 to get rid of that half, and I could take the gt to the other side. And then that's going to give me what I'm asking for. What is the total time of flight? So the general time of flight will be 2u sine theta over g. And you may be asked to have to prove something like that to show that the time of flight is to do with 2 lots of the u value, whatever the initial speed is, sine theta over g. Okay, that is the time it takes for its entire flight. And that works for any initial speed and any angle. Of course, gravity is 9.8. Okay, so what's the range then? If I know that the total time of flight is going to be 2u sine theta over g, the question is now how far have I travelled? Just in the x direction, how far would I need to walk to get to that point where it's landed? Okay, so if it's kicking a football, how far do I need to walk to get to that football? Now we know that when we work out the range, that is to do with the x value. I'm walking across in the x direction. Now I know how long it takes. It's written right there. It was 2u sine theta over g seconds. So what can I do to work out my velocity across here? Remember that u and theta are variables. I don't know what they are, but t, I can substitute that in. And that's exactly what I'm going to do. So I take my x value, which is ut cos theta. I substitute that t value in. And what I end up with is an equation that looks like this. Looks like a bit of a mess, doesn't it? But what's nice about this equation is that 2u squared sine theta cos theta, or just the 2 sine theta cos theta, you should recognise. 2 sine theta cos theta is one of your double angle formulas. So you can use the double angle formula like that 2 sine theta cos theta is equal to sine 2 theta, just to simplify this down a little bit. That's going to get us the equation for the range. U squared sine 2 theta over g. So the range, or the distance you've travelled to get from there to x, would be whatever the initial speed is squared times by sine doubly angle over g. Okay? And again, you may be asked to show and prove where that comes from. So it's important to make sure you're aware of doing it. You can use the Suvat, you don't need to use the vectors, but if you've got the vectors, it does make it a little bit easier to figure out which bits go with which. Okay, because you can see which bits is to do with the x and which bits is to do with the y. Okay, so we want to look at its maximum range. Okay, what's the very maximum range? So say for example, I'm stuck with a certain speed, just there, but I've got an angle that I can change. That's a variable angle. I can shoot it whichever way I like. Okay, what I want to do is work out what the very maximum value of this is going to be. Now, if we think about what we can actually maximize and what we can't, what can we actually increase and what can't we increase when we look at this equation? Now, the u value, if we had no limits, we can make that as big as we like. So u squared is not really going to cause us any problems. We just keep that as u squared because we can set u to be 20 million if we wanted to. Okay, but sine 2 theta is a limiting factor. Because if you think about the graph of sine 2 theta or the function sine 2 theta, if you try putting in theta equals 10 million, the sine of it is still going to be limited between 1 and minus 1. It doesn't matter what value of theta you put in, once you do sine of it, you are only going to get values between 1 and minus 1. So if I want to work out the maximum range, right, the very greatest value of it, this sine 2 theta is going to limit us. We can't get any bigger than 1 out of sine 2 theta. U squared we can make as big as we like. G is limited with gravity, it's 9.8, but this part just here is only going to equal 1. So the very maximum value of our range is always U squared G. Okay, so that's the maximum range. So you may get a question in that exam, which is we can fire it at any angle we like. The speed is, let's say, 10. Then what you can say is, I know what the maximum range is going to be then. It doesn't matter what angle I change it to. The best angle I can get would get me a range of 10 squared over g, 100 over g, 100 divided by 9.8. Okay, and you can work out the maximum range by doing that. Just out of curiosity, what angle would you need to set it to? Okay, so what angle would we need to set it to get this maximum range? Well, the angle we need to set it to is when sine 2 theta equals 1. Okay, so when does sine 2 theta equal 1? You get your calculators, you can do, well, you don't even need your calculators, sine to the minus 1 of 1. Okay, you know that sine graph goes up, it reaches its maximum value at 90 degrees. So when does 2 theta equal 90 degrees? Well, when theta equals 45 degrees. And doesn't that make sense logically? If we want to maximize it, it's best to point it perfectly diagonally. You point it too high, it's going to go up really high and come back down really short. So you only got a very short distance. If you point it really shallow, then it's going to just come straight back down and hit the ground really quickly. Okay, so it makes sense to go somewhere in the middle. In fact, exactly in the middle at 45 degrees would reach your maximum range. Let's look at another example then, or another situation. What about if they ask you the maximum height? What's the maximum height of this in a general form? So there's our height just there. Now what's special about the maximum height? We know that maximum range is when the height equals naught, but what about its maximum height? Now you know, having got some of those questions and what we just talked about, when you're reaching the maximum height, that's when the velocity upwards, so velocity in the y direction equals 0. Velocity y direction equals 0. That's what we're looking for. So what I can do is I can set that equal to naught. I can rearrange it and get my t value. And lo and behold, what I've noticed is it reaches the time at that point just there, exactly half of the total flight time. Right? I could just use that fact, but be very careful. Okay, that's true because it takes off and lands exactly the same height. If this is one of those situations where it takes off and hits the top of a roof up here, that's different for the float for the different times. So be careful. All right. If it's just kicked off a cliff, obviously the maximum height is the cliff itself, but flight time is not going to be half of that. Okay, so you need to be careful. In this case, because it takes off and lands in a perfect parabola, then yes, its flight time at the top is exactly half of the total time. Right, so I've got that. How now do I actually work out the answer then? So I've got my time. How do I work out the maximum height? I can go to my height equation. There it is. And I can substitute in this value. So if I substitute it in there, it's going to get a bit of a mess. It ends up looking like this. Okay, so what happens then? I can see I've got u squared, I've got sine theta there. In fact, I've got sine squared theta, haven't I? Because I've got sine theta times sine theta all over g. So this is going to get me u squared sine squared theta over g. This one, well, that's going to be g squared, but that g and that g will cancel, so that's quite nice. I'm going to get u squared sine squared. So in fact, these two terms are going to be the same. Both of them are going to be u squared sine squared, u squared sine squared, both of them over g. But look what you're doing. You've got a whole one there, take away half of one there. So I've got a whole one, take away half of one, which of course is going to end up being half of one. So you can see it here, and I've simplified it. I've got a whole one there, take away half of one there, is going to end up equaling half. That's where the 2 comes from. Half of u squared sine squared over 2g. Okay, and that's a bit tougher. It's a bit tougher to simplify it, but at least you don't have to worry about double angles. And I just want to show you an alternative to that. So an alternative way to find the maximum height, especially for people that prefer using the Suvat equations in a different way. So the one Suvat equation that you can't use with vectors, but you could have used if you're looking at them individually. So I'm looking at just up and down. Okay, so let's have a look at this. So if I'm resolving in the y direction, in other words, just looking up and down, at this maximum height just here, okay, at this maximum height, I know I can call S the maximum height. Okay, so that's going to be S. Now, if I've got S is my maximum, all right, I've got U equaling U sine theta, so that's my initial velocity upwards. I've got V equaling naught, which is straight up. I don't know what T equals, but I've got A equaling minus G. Notice I haven't got any T in there. I don't really care about T. All right, so it's not a case of having to work out the time of height. I'm looking at just as a Suvat equation, this one. So if I do that now, what's the equation of, or the Suvat equation that links these things together? It will be v squared equals u squared plus 2as. V squared is going to be 0, u squared is going to be u sine theta squared, plus 2 lots of minus g, because that's the acceleration, because it's pulling it downwards, times by s, which is my maximum y value. Okay, so what can I do with that though? I can rearrange it. So I can pull it over to this side, make it a bit easier, u squared sine squared, and lo and behold, my maximum y value, in this case, would be u squared sine squared theta over 2g. And you can see there where some of you may prefer to use Suvat, some of you may prefer just to stick with doing what you're used to with these. It's up to you. You can use both. Just be careful with using the v squared equals u squared plus 2as, all right, with the different vectors. Okay, so well done if you managed to follow all that and got down your notebook. So just pause there if you need any more time. Okay, so what we want to do now is we want to find a Cartesian equation, because as you've noticed with all of these projectiles equations, they form this nice sort of parabola shape. Now, if it's a parabola shape and you wanted to plot it, you've plotted parabolas before, you've sketched parabola shapes before, you've done it since year 1. They are just to do with a quadratic curve. So what I want to know is what would be the equation you plot if you want that perfect parabola shape of your projectile. Okay, so that's what we're going to do. So in other words, we're going to change it into parametric equations. So that's my position vector just there, this one that you're used to. Yes, we've got the velocity and the acceleration as well, but that's just my position vector. And notice that if it's a position vector, I can rewrite it in terms of the x position and the y position. All right, that's how far across we go. That one's how far up we go. So what I can do is I can write them as two parametric equations. The x equals uxt and the y value equals uyt minus a half gt squared. So I can write them as parametric equations like that. Once I've done that, how do I go from parametric to Cartesian? What do I need to do to go from a parametric equation to Cartesian? And again, if you were here, I'd hope one of you would tell me that you change the parameter in here. So we can change it so the parameter t is the subject, and then we can substitute that into there, and that's going to get me my Cartesian equation. So that's what we're going to do. We're going to rewrite the x equation to get this new parameter t, so t equals x over ux, and I could substitute that in to this equation, and I'm going to end up with that. And there we go. That is my Cartesian equation just there. And if you look at it, you can see I've got an x squared, I've got x's, so that's y, and it's y equals. So you can see why I've got a quadratic equation just there. All right. Notice it's also got no c value. That's because it goes through 0, 0. Okay. So I got my equation. I could make it a little bit neater, couldn't I? So there we go. I've done that. Uy of uxx minus g over 2ux squared x squared. It's my quadratic equation. So if I've got an initial velocity, ux and uy, I could definitely type that straight in to a graph plotter and I would get this beautiful parabola shape. Okay. Right, but we also know we can do it in terms of a speed and a direction. Now this is going to be the same bit of work, but it's worth just following it through again. That if I've got it in this form, speed and angle, then I can still get my x's and y's. So x equals the top one, y equals the bottom one. I can still write the parametric equations. So x is going to be ut cos theta, y is going to be ut sine theta minus a half gt squared. So I can still got my x's and y's. Now what I can do with these equations is exactly the same as before. It's going to be a little bit more messy because you've got some u cos theta and u sine theta floating around, but the actual maths is the same. How do I make t the subject? I can rearrange it so that t equals x over u cos theta. If I now substitute that into this one, what I end up with is this equation going to this. And there again, I've got my quadratic equation done now. The parameter t's gone, so it's definitely a Cartesian equation. It's just not very neat. So I can neaten this up. Oh look, the u values here cancel out. So that's quite nice. So u doesn't really come into this one at all. I've got a sine over cos just there. So that can cancel down to tan if I wanted to write it as tan. This one here, I've got an x squared, great. I've got a u squared. I've got 1 over cos squared. So I could change that if I wanted to. All right, so I could definitely change that to a sec squared. So I've got tan theta and I've got a sec squared theta going on here. So I could change that into whichever form the examiner wants. So sometimes the examiner might say, I want it left in that form, fine. Sometimes they might want to write it in terms of tan and sec squared. That's okay as well. Notice I've just put the x squared g and the 2u squares together. And sometimes you might be thinking I can play with this sec squared and then get tan squared just there. Okay, because I know that as a fact. that 1 plus tan squared equals sec squared. So really, I might be able to write it like that. And yes, you could expand it and have it as tan squared, but the examiner might expect you to say, look, can you follow it through to any of these? Now that's the top end of your projectiles questions. In the likelihood in your exam, you're going to get one like you practiced before in the textbook, where they're going to give you a nice starting position and you've got to work out things like maximum height, maximum range, what time does it reach this point, and things like that. But if they are going to ask you the harder top end questions, then you need to go back and just practice doing these sorts of things again yourself. Okay, and every single time you come to practicing one of these questions in your work packs, what I would recommend you doing is trying to do it yourself off by heart, not just diving for your notes every time and copying it through. Okay, so practicing both 1.5 and 1.6, and that should end your projectiles questions.